Hello and welcome to our channel again. So here I am Suraj with a new video of mine where we'll discuss about another very important things in the quantum mechanics, which is canonical transformation. So what exactly this things? Okay, so this is a very new terms for yours, but you know this doesn't have any specific meanings. So using the basic quantum mechanics, we are going to see that what exactly this canonical transformations means. So the thing is that we know that we have discussed about in a previous video about the operators in the quantum mechanics, that what these particular operators are. We have discussed about the position operator, we have discussed about the momentum operators, we have derived some of the, like this is a representation of a momentum operator, this is a representation of a position operator, this is a representation of a kinetic energy operator. So operators in quantum mechanics are what we have discussed in the previous video, but not what we are going to study is that basically in the position and the momentum cases what we see is that the when we suppose that we apply the momentum of suppose that we apply the position operator to the momentum operator and then to a particular system psi. Okay, so on a particular system wave function. So and suppose that we apply the momentum operator onto a position operator and then applying this particular quantity and particular wave function. So is this same? It means I want to say that is these two particular quantities are same, applying firstly the position operator to the momentum operator, position operator to the momentum operator, or applying the momentum operator to the position operator and then applying it to the wave functions. So is this true that these things in the quantum mechanics? So the question is no. So the question is no. This seems like a very pretty simple in the basic mathematics, but no, we are dealing with quantum mechanics, which is some sort of a very abstract. So in this case these two cases are not equal, these two cases are not equal, that applying the position operator first and applying the momentum operator first will change our things. So that's why this is very important to understand that these things are not true in the quantum mechanics. So let's see what will happen. So generally if the any of the functions do not equals, like in this phase, that applying firstly the position operator to the momentum operator and then the momentum operator to the position operator, we say that these two operators do not commute with each other. We are saying that these two combinators do not commute with each other. It means this is not simply the commutators means commute means this particular quantity is not same as this particular quantity. So this is basically the meaning of the commutation, that these particular two quantities are not commuted, means this is not equals to this. So there is a sign for the commutator. So if there's x operator and the momentum operator, so it's denoted by p hat. Okay, so this is the sign of the commutation and this is equals to the x operator momentum operator and minus momentum operator x operator. So let's understand it in a pretty way. So if we are dealing with quantum mechanics, but let's assume that we are dealing with no any quantum mechanics but simply numbers. So if you are simply dealing with numbers and there is a now suppose that there is a 1. Okay, so first of all we apply 2, it means we multiply 2 with 1 or we multiply 1 with 2. This is same, this all will give the value 2 and 2. It means this shows that relationship, it means these two particular quantities are true. So let this that we apply this, this is a and let this is b. So it means they do not commute with each other. It means these two quantities are equal. Applying 2 first or applying first form make no differences. And the commute, this is a sign of a commutator, remember. It means this is a sign of commutator. It means doing this particular thing, it means a and minus b. So if a is equals to the b, the commutator of the operator a and b, the commutator of the operator a and b is equals to the 0. So just like in this case we have mentioned that this is not equals to this. It means x hat p hat minus p hat x hat is not equals to 0 and these two quantities are not 0. So what is the quantity that when we obtained when we apply these things? So let start the derivation, that what happens when these two particular quantity minus what quantity we get this. So what we see is that let's take any system. Let's say we take the system's psi, which is a wave function. So what we'll do is that we just started applying those operators. So first of all what we are going to do here is that x okay, x operator and p operator and psi. So applying this particular quantities, so applying this particular operators consequence, what we got is that this particular quantity is, then the x operator and p operator is equals to the iota, which is of the negative h cut, and del psi divided by the del x. So this is the quantity that we get. So this is our first case, okay. And the second case will be, the second case is like this, when we are applying the momentum operator first, not the position operator, and then applying it to the wave function or wave functions. So this means applying the momentum operator iota h cut negative and del upon del x. So here are two quantities that we have to differentiate, x and psi. So we will use a very simple product rule in the differentiation. So this quantity will give minus iota h cut. So this will minus iota h cut del psi first del x, and then minus, we will get, this is iota h cut psi, and here del del, sorry, psi nahi, here it is del x divided by the del x. So differentiation of, so now we will, if we resolve this particular things, what we get is that this is equals to the minus iota h cut, sorry, I forget, here I have x forget, so let's write here x cap, okay. So iota h cut x cap del psi divided by del x minus, so what is the differentiation of x, what's the partial differentiation of x with respect to x? So it is equals to the 1. It means this particular quantity here now becomes iota h cut psi, okay. So now we have done, we found out this and we found out this. So you can see here that this and this are not equals, this and this are not equals. Here is an extra term minus iota h cut psi in this thing. It means these two things are not similar and they do not commute with each other, and they do not commute with each other. So what we now do is that we have to find out the value of the commutator relationship between the position and the momentum. And what we can do is that let's apply this formula, okay. So applying this formula, what we get is that here, very important thing, that x operator and p operator, okay. So here x operator and p operator, I'm not putting hat here, so just see that it's the position operator. So x of p, which is this, okay. So this is, I'm writing it here, minus x cap p cap iota h cut del psi divided by the del x, del psi divided by the del x, and here is minus, and minus minus become plus here, and minus minus become plus here, which is equals to the plus iota h cut x cap here, and del psi divided by the del x, and minus minus again plus here, and it is equals to the iota h cut. So you can see that these two quantities are similar and we just cut out each other. So what we found is that x and p hat is what equals to the iota h cut, okay. Why we neglect psi here? Because we have just, we are going to just show that the relationship, that why we just neglect psi. It does not mean that just we cut out the psi here. It's, so just forget this psi, because we are going to show the relationship between this particular two operators. So the thing is that we obtain this particular final value, and this is a very important thing, and this transformation is known as the canonical transformation. This transformation is known as canonical transformation in the quantum mechanics, and this is a very beautiful transformation which tells that how the position and the momentum operators, when we have changed the order of applying these operators, has a very big difference in the quantum mechanics, as you can see here. So you can see that the commutator relationship between x and p cap is not equals to the 0, as in the case here. But here is the case because 2 into 1 is equals to 2 and 1 into 2 is equals to the 2, and it is same whether applying multiplying 2 first, whether applying 1 first, it is not the make differences. But in quantum mechanics it makes differences, and we can see here that the commutator relationship between the position and the momentum is not equals to the 0, but it equals to the some quantity known as the iota h cut, and this is a very beautiful transformation in the quantum mechanics. So this is a short video of mine where I discussed about the very important canonical transformation in quantum mechanics. And you know, this particular transformation is very useful when we derive our harmonic oscillator and any other things. So just keep the formula in the mind because this is very important. So thank you for watching my video on this small lecture on the canonical transformation and its derivation.